loud, take it away.
Okay. Hello everyone. My name is Joel, and today I'm going to my first project, Tantivy. I'm going to start by a very short word about me. I'm a French developer living in Japan. I started this project around 2 years ago. It's a project that got started where I was working at the training opportunities that you might know. Right now I'm working as Google, and I've been asked specifically to be very clear about that this project is not a really calculated business. I think there are some of the might have questions at the end of the presentation about the way to propose search. I will not answer any of those questions. Apologies for that. Please do not think, hey, Google is actually using Tantivy for their search or something like that. I could be fired, so not related at all. Alright, so what's Tantivy? It's a search engine library. I'm going to assume here everybody in the room is familiar with Lucene and is coming here to hear a lot of information about the Lucene ecosystem. So you're probably familiar with Lucene, Solar, and Elasticsearch. Within this trinity, Tantivy is closer to Lucene. So it's very, very close in concept to Lucene. By which I mean, if you want to build a search engine using Tantivy, you're going to have a program that uses Tantivy as a library, and you're going to use all of the building blocks in Tantivy to actually get the search engine in there. It's not like an off-the-shelf solution on which you run a server and everything is ready. It's written in Rust, so I don't know if everyone is familiar with Rust. If you're familiar with Rust, can you raise your hand? Oh, wow. This language is getting popular, I guess. So for those who are not familiar with Rust, it's a programming language that is kind of young, and usually people will try to love it. Within all to give you an idea of what it is, you can, most people will take me for that. You can consider it as a C++. So the code that you write is basically safe, and your program is very similar. Like it's very difficult to tell about Rust code from C++ code if you're just looking at the assembly code generated. You will get the exact same performances. So you get like safety, and you get a great ecosystem, and you get great tooling, and the syntax is better. It's simpler to learn. So a bit of C++, an okay definition, I think. So Tantivy, what is it's using LLVM, which is awesome because it means that Tantivy can actually compile on, of course, Linux, macOS, Windows, but also it can compile on platforms that are not x86 supported, so you can actually run Tantivy on ARM, I've done that before. And I actually even compiled Tantivy for WebAssembly once. So that's not something that I probably talk about too much because there is no support for shredding right now in WebAssembly, but at one point, maybe Tantivy will be an alternative to run such a thing in your browser. It's still cute. It's very important for me to keep the number of lines quite small. There's only 30,000 lines of code. Even if you include all of the different crates that I have to write for Tantivy. It's very important for me because, as I told you, it's a pet project, and you like to bet a pet project, so it's very small and cute. And also, ideally, I would love in some future to have companies that are considering building their own search engine from scratch if they have, for one reason or another, if they cannot use Lucene for that project. Rather than starting from scratch entirely, I love them to at least consider using Tantivy. And that means that having a small code base makes it possible for people to actually embrace the code and own it, and own it and work with it. It's fast, so I put a link on the benchmark here. I think we won't have time to go through the benchmark, but there is an interesting benchmark that breaks down the performance of Tantivy per query. So you can look for different kinds of query. usually it's doing pretty well. You can only compare it with different versions of Tantivy and CD7 right now. But what's really interesting is that you can actually identify, oh, for this query, machine is actually faster, what's going on there. So that's a great way for me to explore different optimizations that are in the C and do not exist in Tantivy. I can know what would be the next step for Tantivy. And it was the other way around. For some queries, like Tantivy is abnormally faster than you see. Maybe that's a good hint that there is some optimization that is happening. So I suspect that everybody in the room is more interested in this thing and Elasticsearch and some of the other strategies. This is one for the implementation. So I'm not going to talk too much about Rust. Actually, I'm going to from now on, we're going to build a search engine together. And as a matter of fact, Tantivy is strongly inspired by Lucene. So all of the stuff that we're going to talk from now on are very valid for Lucene as pretty much the same design. So hopefully at the end of this talk, you should be able to understand Lucene maybe a little bit better. So yeah, let's build a search engine together. Most effectively, our objective will be, we want a search engine that is, I'm trying really hard not to use the word scale here, because we are still talking about a search engine that is sitting in one machine. But we want to be able to search and index terabytes of data, a lot of data, on a machine that is that only have gigabytes of RAM. So we want to make sure that all of the stuff that we are doing are solid and they don't require you to have gigantic amount of RAM. And so Tantivy can do that. I actually tested it. That's something that I did. So right now we are at Tantivy 0.8, and I did test the use case with Tantivy 0.6. And what I did is that so there is this publicly available dataset called command proof. And what it is that it's a kind of a snapshot of a core of the web. And it's a pretty large one, a very decent one. It's around 3 billion pages. So I took this snapshot, I downloaded it with, to be accurate, I downloaded half of it. I downloaded half of it using my own personal internet connection. I think my internet provider pays me. It took like around 1 month full time. I'm in Japan, so we have like optical fiber and stuff, so they pretty good connection to the skill. Yeah, and I wanted to test if I could index it, see what happened, because like it's a very good test to do that like in your home, especially like I bought a house in Japan and the electrical network was not really great for my usage. I mean, I'm French, so I drink coffee and I have toast in the morning, and when I would switch toast at the same time, I would always have a pocket in my phone. That's a great test for such a joke, mixing stuff. So yeah, so I did that, and I deployed the Python library on top of that to, well, basically the goal of the Python library is to extract like you give it a query and there is a placeholder. So for instance, you could say French people are, and then you ask for all of the adjectives that follow this sentence. And so the two libraries together, Tantivy plus this small NLP library, made it possible to look for on the internet the most common adjective associated with French people. I think it's pretty accurate. Okay, so let's move on. So to build something that was complex search, usually means that you're going to have to build that. It's the most common way to do complex search.
Can you check if you're muted, please? Green. No, it's green.
All right. Okay, so usually that means that you're gonna want to build an inverted index, and an inverted index is simply something that associates to each term a list of sorted list of a sorted list of the queries. And this simple data structure is sufficient to actually compute any kind of Boolean query. So I'm going to explain rapidly how intersection works. So assuming that we are trying to find all of the documents that are matching the query René and Magritte, we're going to have like these two posting lists. We take the first one. The first document of the first one is 2, and we are going to seek into the second posting list for the document 2. So by seeking, what I mean is that we are going to do exactly as if we were advancing, going through scanning through the second posting list, and we are going to stop at the moment where we find a document that is greater or equal to the document. If it's equal, then that means that 2 is in the intersection. If it's greater, then it's not. So here it's not, and we found the document 5, and we are going to do symmetrically. We are going to seek for 5 in the first posting list. Here we go. 5 was found, so it's going to be in our output. We can advance the first posting list, and now we are seeking for 7 in the second list, and so on and so forth, until we reach the end of one of the posting lists. So the only takeaway there is that if you want fast intersection, you need to have a fast way to seek through the posting list. For union, we could use the same strategy. Like basically, it's like the merge. Everybody has a different name for this algorithm, but we could merge those two posting lists and get the union. But that's actually inefficient. So I'm using the same trick as Lucene does. The idea is that you prepare in advance some kind of bit set here. And so just for the sake of this slide, the bit set is actually of length 8, but in Tantivy, we're using 4096 bits, so it's much larger. And what we do is that we are going to take the first posting list, and we are going to we are going to append all of the docs that are between 2 and 2 plus. So this horizon, in this case, 8, but in Tantivy, 4096. And we append those documents in this bit set. So in this bit set, the first bit will mean 2, the second bit will mean 3, and so on and so forth. We do that for the first posting list, and we do that on the second time on the second posting list. Here's what we get for bit set, and now we can flush it. So we transform basically this bit set into the document that it represented. So it can be done quite fast because your CPU usually has an instruction to pop the lowest significant bit out of a 64-bit word. So you just pop it and so on and so forth. All right, so that's how an inverted index is used to compute Boolean query. Now the question is, how do we represent that on disk? So Tantivy is relying on mmap for all of its I/O, and when you start Tantivy, the only thing that it does is basically mapping all of the file of the index, so it goes really, really fast, and it's ready to go. So we don't have to load any data structure and put that in anonymous memory and like have some kind of hash map in anonymous memory. Everything is on mmap, so the startup time is very, very nice. But that means that we need to have data on the disk that is usable as is. For Java people, anonymous memory is more or less like the heap. So
So the first data structure that we are gonna have to have in our index is a term dictionary. So a term dictionary our term dictionary will be broken down into two steps. One step will associate the term, so like the sequence of bytes associated with the term, to some kind of term ID. And then we're gonna have another data structure that associates the term ID to some kind of term info structs that basically like have pointers to files and like the beginning of the posting list, for instance. I'm not going to talk about the second data structure because it's boring, but let's talk about the first one. So how do we go from terms, sequence of bytes, to a term ID? So if you are actually trying to build your own search engine, you will have two broad kind of family for this solution. One could be like hash-based in general. Maybe you will go fancy and have like perfect hash or something like that. It's a very nice solution in the sense that you would get like very fast lookups, and especially if you don't have much RAM and everything is sitting on your hard disk, you will probably require very little I/O to do that. Your hash map will be able to send you directly in the right place on your disk. Another solution is using like a tree-based solution or like a trie. So this will require. This will use slightly more CPU, and you will have a lot more random I/O. So that kind of depends on the layout of your data, but you tend to jump from one node of your trie to another node of your trie. So that might be a lot of six if your data is on your disk. But it has a lot of benefits. So one benefit is you can iterate through a range of keys. Naturally you will probably use term ordinals. So by term ordinals I mean if Arabica is your first word in your dictionary, then it will get term ID 0. The first word when sorted lexicographically, and then the second word might be something starting by a B, then it will get term ordinal B, term ordinal 2, and so on and so forth. So term ordinals will, your term ID will be sorted exactly the same way as your terms. That's a very nice property. But more importantly, you can do an intersection of your trie or your trie-like structure with a DFA. So are you guys familiar with what a DFA is? Okay, we'll still explain it a little. I actually made a mistake in the DFA here, but so that's one. So DFA stands for deterministic finite automaton, and that's one way to implement regular expression. So you can transform any regular expression into an automaton like this one, and the way it works is once you have it into this shape, then matching a string on this automaton means that you're going to consume every charge in your string. You start in the state over there. I was hoping I could point at stuff, but you can jump. So you start in the white state over there. And let's say that you are trying to match carousel. Your first char is C. You look at the outbound arrows that are emitted by the state you are in. One is labeled with a C, so that means that after consuming the C, I'm in that state, the yellow one. And then carousel, second letter is an A. I'm going to follow this letter, this arrow, and I'm in the blue state. R, I end up in this state, and Ucel until the Uc, I guess, without the L, will be following the arrow with a star over there, and then the last L will bring me to the end state. So it's really nice because I'm advancing one char at a time. I just have to look at the state of the end state of my string to say whether I matched or not. I mark the states that match by a double circle here. So our trie looks like this, and it's actually possible to match this DFA over the try very efficiently. So I'm going to show how it's done. So here, if we consume the C, we end up in the yellow state, just like for carousel. If I consume the A, I end up in the blue state. If I get a B, then I end up in this gray state, which happens to be a sink. So the sink is a dead end. We will never match if we reach this state. We don't need to see what happens with the following characters. And that's great because that means that all of this subtree, we don't care about it anymore. So for the purpose of fitting things into the slides, this try is very simple. But you can imagine that maybe there is a gigantic tree that is a child of this node. And we just cut that. So that's much, much faster. And now we want to match M. We don't have to recompute what is the state required for A. We can just look at the state of A before. So that's blue. And we see that we are in the sink state again. And so on and so forth. So we are just putting colors over our try to guess which term in our dictionary are matching our deterministic finite automaton. That means that I can go through all of the terms that match a regular expression, but also I can get very rapidly all of the terms that are at Levenshtein's distance or edit distance of 1 or 2. So that means that if you are asking me, please stream me all of the terms that are one typo away from what I typed, I can do that very, very efficiently. So Tantivy is using a tree-based solution. It's actually using a finite state transducer. Lucene does too. And I didn't have to code anything. The Rust ecosystem is nice enough that somebody already coded a very nice implementation of finite state transducer. I will not explain how it works because I didn't code it. But the thing that you might want to know about it is it's pretty much like a try, except that nodes can share suffixes. So a try will never have an error that goes like this, right? So because it can share suffixes, you end up with something that is slightly more compact than a try. And that's always a very nice feature when you're playing space with your RAM. Now let's talk a little bit about how we are going to encode posting lists. So posting lists are a lot of integers. It's going to take a lot of the size of your index. And you're going to want to compress them. Integer compression is a field that has been well studied. There is a lot of solutions to do integer compression. I put a chart over there, but basically my point here is you have a trade-off between something that is compressing a lot. So it's always like that, right? You have to choose with something that compresses a lot and something that is very fast. Another thing that I need to point out is basically all of the algorithm over there, and yeah, all of these, all of the best algorithms, they're all using SIMD instructions. So SIMD instructions are instruction on your CPU that makes it possible for you to process 4 or 8 integer at a time. So that's something that actually Tantivy is using a lot. So Tantivy is actually using this guy over there. So it's a compression scheme that has been designed by Daniel Lemire. I recommend you to read his blog. It's always very interesting if you're interested in things related with search or data structures. I used to depend on his library actually in C, and I removed it because I prefer to be entirely in Rust, and I re-implemented it entirely in Rust. The gist of it is, like many of those schemes, your posting lists are increasing, so it starts by doing something called delta encoding. So instead of compressing your integer directly, what you do is that you take the difference between two consecutive integers and you get something that is much smaller. You take a pack of those, in my case, blocks are 128 integer long, and out of those 128 deltas, you look at the one that is the largest. So I think in this example that should be this one, that's 16. And you notice that it can be represented using 5 bits. So what you do then is that you represent all of your deltas over 5 bits, and you just concatenate this version. So that's called bit packing. So I described what was the solution for like the scalar version of bit packing. What I do is actually I use SIMD instruction for that, and I do that with 4 integers at a time. So I decode 4 integers at a time, and the algorithm really looks like this trick that we were using at school to avoid like writing lines when we were punished by our professor. So it uses exactly the same algorithm as the scalar solution. You just use SIMD instruction in place of like the scalar instruction. It's very, very simple. And there is an interesting improvement compared to the method that existed before Daniel Lemir's paper, which is the algorithm also take advantage of the fact that as we are decoding those integers, we end up at one point where we have one register with the delta that we are decoding, and we can decode the delta using SIMD instruction as well. So this is also a SIMD instruction. And we do that at the point where they are already in the register, so it goes really, really fast. And we're talking about, when I say fast, to give you an idea, I'm talking about 4 billion integers a second. So we are already we're flirting with the bandwidth of your RAM, basically. So I told you that Rust was nice and was able to compile like very efficient code, that it was very close to C++, and so I wrote that in Rust, and this is assembly that is generated. I'm not going to tell you that I understand what's what's in there. But the important point here is that all of the like long-looking instruction over there, every single one of those is working on 4 bytes at a time. And you will see scalar instruction maybe here, here, here. So the assembly code that is generated is really as good as possible. It's very, very close to, it's probably exactly the same as what we had in C++. So I think we talked this morning a little about BM25 and TF-IDF. This requires to, so those are like the scoring, the default scoring function of Lucene. Tantivy comes in with BM25 also. This requires to have access to the term frequency as we search. So when we match a document, we need to have access to the number of times a term appears in the document. And it's nice to have good locality for that. So we actually interleave blocks of doc IDs with block of term frequencies so that we are likely to have it in a nice cache at the moment where we are reading the as we are doing the match, as we are running the query. So we have one block of doc IDs and then one block of term frequency and so on and so forth. Each block is representing 128 blocks. So unfortunately, postfixes are not always exactly a multiple of 128 blocks. So the last one is using a different compressing scheme. That is not interesting. And so we also need to have the information of how many bits are used to encode each block. And we also would like to have some way to avoid decompressing this block if we are running in intersection, for instance. Maybe the document is not in this block, and in that case we would like to entirely avoid decompressing it. So for that we have another structure on top of that that allows us to precisely skip and go to and decompress only the blocks that might be interesting. We're gonna talk about something else now. So I said in the beginning of the talk that we wanted to be able to index an arbitrarily large amount of data. I use the word terabytes. And that's a big problem because if we have a reduced amount of RAM, how are we gonna be able to build like this nice data structure on disk? We have another problem, which is people might like create an index and they want to add new documents. We want something that is dynamic. We want to be able to add documents to an existing index. That's another problem. It happens that the solution is the same for both of these problems. So just to refine the idea of why it's difficult to add new documents in an index like that. So the data structure that I described to you on disk is extremely compact, right? Everything is super compressed. Everything is laid out on disk, one after the other. So it really, if it was a bookshelf, it looks like this. And if you're in front of a bookshelf like that and somebody gives you a book and tells you to put that in the library, you're going to suffer. You're going to have to move everything away. It's a nightmare. What you want is to have something that looks like that if you want to update your bookshelf all of the time. So generally speaking, there is a trade-off between being dynamic and being compact. So there is a nice trick that exists in many databases that is called the logarithmic method. The idea will be we're going to have like compact bookshelf like that, but we are going to have many of them. So the way it works is the user will tell Tantivy or will tell Lucene, hey, Tantivy, I will give you a budget of, let's say, 300 megabytes. And this 300 megabytes will be used for the dynamic bookshelf here. So there's going to be a big bookshelf, and people will add books into that until the bookshelf is full. Once the bookshelf is full, we are going to transform it into a very compact bookshelf. So I'm going to stop with the image here, but basically we serialize our dynamic data structure into the static data structures that I described before. And this piece of like very compact index is called a segment. So that's a word that you probably heard in Lucene, but that's a segment. And both in Lucene and in Tantivy, there is a strong architecture choice. A segment is basically an independent index. So you could literally like pick a segment and copy it into another index, and it will run just the same as long as the schema are the same. That's a very interesting property, actually. So if we do that, we are going to end up with a lot of compact segments, and maybe that's not optimal. If we have 1 terabyte of data, that would be a lot of small segments. And when we do a search, we are going to have to do as many lookups in the dictionary, and that's very inefficient, right? So on the background, we also have a process that merges those segments together, and you can actually control, you can define on your own as a user what is a like strategy used to merge these segments, but it comes with a default strategy called the long merge policy, and the heuristic behind it is just we try to merge, by default it's going to be 8 segments that have about the same size, and yeah. So this technique is also really nice because that means that we can do multi-threaded indexing very, very easily. So Tantivy asks you how much data you give as a budget and also how many indexing threads you want to use. And then when you open the document, what you are doing is that you are appending the document to a document queue, and you, in the background, and you don't control it, but it says your given number of indexing threads that are consuming this document queue and that are populating these dynamic data structures that I was talking about. And once they reach their capacity, then they're gonna serialize the segment. So the serialized segment is the very compact data structure that we use in the end. And some merging thread will merge those very transparently. Yes, thank you. So there is a bunch of pros and cons to this. One problem that is very evident when you use Tantivy, and I think it's still true for, to some extent it's true with Lucene, is that when you add a document, it's not searchable right away. So it's quite puzzling for people who are using SQL database. Because we decided to have our segments to be independent index, they do not share any dictionary, and that's sometimes that makes like specific usage of search difficult, not to be able to actually merge the result from the different segments very easily. Yeah, there is not one dictionary. I didn't talk about deletes and updates, but those are an absolute nightmare. It's very complicated. Yes, that's pretty much all I have on this slide. And then the pros will be the index throughput is actually excellent. If you can batch stuff, if you don't have to commit all of the time, you can re-index a gigantic amount of data. So I think on my laptop, I index Wikipedia in, I always forget if it's 2 or 3 minutes, but that's the amount of English Wikipedia. But that's the speed we're talking about. That's, Wikipedia is like a tiny benchmark in search. It's not a big data set. Yes, so segments are independent index, so you could decide to actually do your indexing on Hadoop and just copy the file of the segment in the same place, and everything will work just the same. Or you could decide to do a distributed search by sending the segment and dispatching them. It's really just copying files. It's very transparent. And because we write files and then we never touch them again, we just write very large file and then they're read-only. There is no problem of locks or anything. Readers just read the file and nobody is touching them, so it simplifies a lot of my work. I have a bunch of slides there. Let's keep them so that we have a bit of time to ask questions. So, do you guys have questions? Yeah.
I'll try to say it out loud. Lucene is a little bit of a corner case for Java. Okay, it's like basically a library which is difficult for Java to handle because there's lots of low-level stuff going on in Java. So what about your project and Rust? Do they fit together, or did you find trouble using Rust as you evolve?
So yeah, I wanted to see the little card. So the question is Rust and building a search engine a good fit, I guess, with especially in contrast with Lucene and Java. So I would say yes. So the main benefits that I get from Rust, I guess, compared to Java is first I can access SIMD instruction. Second, I have a lot of control of, I know when I write code whether I'm going to get static dispatch or dynamic dispatch. That's something that is extremely hard in Java. You never know what happens. Also, all of the things like mmap being a nightmare in Java, it's something that I don't have any problem about. I don't know if everyone knows what I'm talking about, but Basically, when you're working with offit memory in Java, like if you are mapping a huge amount of data and you have very little data that is on your heap, your data will be unmapped only at the moment where the object that is holding the mmap thing is garbage collected. And garbage collection happens only if your heap is actually like kind of full. I think that's a big problem with Java. So some JVM give you a non-official Java API to unmap stuff. Some people just like decide to use GNI call to do the mmap. Well, I never have that kind of problem with Rust. Everything I'm working with C or C++. And when I started this project, I didn't know Rust at all, and I started Tantivy to actually learn Rust, which is a bit stupid and crazy. So I already knew C++, and I had done a lot of Java as well. And after around 2 weeks, you don't have to believe me, but I was more productive in Rust, and I felt safer writing code in Rust than I was in both Java and C++. Yeah.
Can you explain the name and the logo of the horse?
Mm-hmm. So Tantivy is an English word. I often do that actually. I like choosing English words that nobody knows as project names. It's actually not bad at all for SEO. And yeah, people learn a new word, so everybody's happy, right? So Tantivy means at full gallop, hence the horse.
Okay.
And I drew the horse myself. I think that's one of the best achievements in the project. Yes?